Hello, welcome back. In this video we'll discuss construction, working and characteristics of LED. LED stands for light emitting diode. It is an abbreviation for light emitting diode. Essentially it is a PN junction. The difference between an ordinary PN junction diode and an LED is that both P and N materials are heavily doped. The junction is formed between two heavily doped P and N materials. In a circuit, the LED element is shown using this symbol. This will be similar to the diode symbol except for these two arrows emitting out of this side of the triangle. Along the vertical line side you have the cathode. The terminal on the base side represents the anode. In an LED, light is emitted due to the recombination of electrons and holes. Light will be emitted in a direction perpendicular to the plane of the junction. Since light is emitted in a direction perpendicular to the plane of the PN junction, these LEDs are also called as surface emitting LEDs. LEDs, they operate in forward bias condition. To find the wavelength of the LED, we need to know the band gap energy, because the energy of the emitted photon will be approximately equal to the band gap energy. We know that E is equal to h nu. If Eg is the band gap energy, then we can write Eg is equal to h nu, where h is the Planck's constant, nu is frequency of the radiation, emitted light. Since we know C is equal to nu lambda, we can write nu as C upon lambda. So here we write Eg is equal to hc by lambda. This implies wavelength lambda of the light that is emitted from an LED is hc upon Eg. Please note that in the numerator we have two constants. One is the Planck's constant, the other one is speed of light c. So their product also will be a constant. So a constant divided by Eg will give us the wavelength. So largely the wavelength of the light emitted from an LED depends on the band gap. If the band gap energy is small, we get longer wavelengths of light from the LED. On the other hand, if Eg is quite large, then we get shorter wavelengths from the LED. Now we shall look at the construction. LEDs are constructed in this fashion. We'll have a gold film or a metal film which acts as a connector and as a reflector. So the gold film at the bottom of the LED will act as cathode and also as a reflector. Over the gold film you have a substrate. Over the substrate we grow N-type semiconductor using epitaxial method. A substrate is a material surface on which a crystal can be grown. Epitaxial method is a method using which crystals can be grown. Over the N-type semiconductor, we have a thin layer of P-type semiconductor. P-type semiconductor layer is grown using the diffusion technique. Diffusion technique is another method to grow the crystals. Over the P-type layer, we have the metal contacts that will work as anode. In the anode, you have a circular aperture or a hole from which light is emitted from the LED. This aperture is filled with epoxy resin because the light emitted from the LED, it might undergo total internal reflection due to the refractive indices of the P-type material and the surrounding air. The refractive indices of the P-type material and the surrounding air may satisfy total internal reflection for the given wavelength for these two refractive indices, and the total internal reflection can cause absorption of the photons because the light is reflected back towards the junction. To overcome the total internal reflection, we use a thin layer of epoxy resin. The epoxy resin acts as a refractive index matching fluid. Thereby, it prevents the total internal reflections. we have taken the p-type material as a thin layer because the emitted photons should not be reabsorbed. Gold film is used as cathode. It also acts as reflector. Over that you have a substrate, and over the substrate n-type semiconductor layer is grown using epitaxial method. Over the n-type material, a thin layer of p-type semiconductor is grown using diffusion method. Over the p-type material, you have metal contacts for the anode with a circular hole for the light to come out of the LED. The aperture or the small hole is filled with epoxy resin to prevent total internal reflections to take place. Now we shall see the working. When a potential difference V is applied across the junction, the potential barrier gap is reduced due to the applied forward bias. Under such conditions, the electrons will be injected into the p-type material. It is called as injection because on the p side, electrons are minority carriers and holes are the majority carriers. So the process of transmitting electrons from n-type material to the p-type semiconductor side is called as minority carrier injection. This is possible because the electron's mobility is high. A similar injection for the holes into the n-type semiconductor is negligibly small. The hole injection into n-type side is negligibly small. The reason is mobility of holes is low. When the electrons are injected into the p-type material side or the p side, the electrons and holes, they recombine to produce spontaneous emission of light, and this light will be incoherent. So the mechanism essentially is the recombination of electrons on the p side with the holes will give rise to spontaneous emission of light, and this light will be incoherent light, and this effect is called as injected electroluminescence. The luminescence is because of the applied external biasing. So when the external bias is applied, electrons are injected into the p-type material side. There they recombine with the holes to give rise to spontaneous emission of light, and this process we are calling as injected electroluminescence. Recombinations are of two types. This is governed by the choice of the material used for the p-n junction. The first one is direct band-to-band recombinations and indirect band-to-band recombinations. For short, they are also called as direct recombinations, indirect recombinations. In most of the LEDs, the amount of light emitted is directly proportional to the forward current. Intensity of light is proportional to the forward current. Now we shall look at the characteristics of LED. First and foremost characteristic is color of the light emitted from the LED. The emitted color depends on the material that we choose to develop the PN junction. If gallium arsenide is used, it emits in the infrared region. If gallium arsenide phosphide is used, then you get the light in yellow color. Similarly, if one uses gallium phosphide, then can emit in red or green. And the forward biasing required for a typical LED is about 2 volts. If you plot the forward voltage along the x direction and the current through the junction along the y direction in milliamps, for a typical LED, the IV characteristic curves look like this. Each one of them corresponds to a particular family of LED. Now we shall look at the applications of LED. The first application is they can be used as source of light. They can be used in optical communications. They can also be used in display panels. In this video, we have seen what an LED is. The LED is an abbreviation for light emitting diode. A light emitting diode is a typical PN junction diode. The difference is both P and N materials are heavily doped. In a circuit, LED can be represented using this symbol. Light is emitted in an LED due to the recombination of the electrons and holes. Since the direction of the light is perpendicular to the plane of the junction, these LEDs are also called as surface emitting LEDs. Always the LEDs are forward biased. We have seen how the wavelength of the LED can be calculated. The wavelength lambda is equal to Hc upon Eg, where Eg is the band gap energy of the semiconductor used for fabricating the junction. We have seen the construction of the LED. A gold film will be there. Over that you have a substrate. Over that we have the N-type material grown using epitaxial method, and above the N-type material a thin layer of the P-type material is grown using the diffusion technique. Over the P-type material we have a metal film which acts as contact for the anode. The metal film will have a circular aperture through which the light is emitted, and the light is emitted perpendicular to the plane of the PN junction. The aperture or the hole is filled with epoxy resin to prevent total internal reflections. We have seen the working of the LED. If V is the applied potential difference across the junction, the potential barrier is reduced due to the forward biasing. Under such conditions, electrons will be injected into the P-type material. Since electrons are minority carriers and holes are majority carriers on the P side, we call it as minority carrier injection, because we are injecting minority carriers into P-type material, that is the electrons into the P-type material, so we call it as minority carrier injection. This is possible because electrons are having high mobility. The reverse, that is hole injection into the N-type side, is negligibly small, reason being mobility of holes is low. Electrons and holes, they recombine to produce spontaneous emission of light, and the emitted light will be incoherent. This mechanism is called as injected electroluminescence. We have seen that recombinations are two types: direct recombinations, indirect recombinations. The intensity of light is proportional to the forward current flowing through the circuit. We have seen the characteristics of the LED. We have seen the three major applications of the LED. They can be used as source of light, they can be used in optical communications, they can be used in display panels. Thank you.